All right, let's get right into it. Today, we're talking about something truly amazing, a point of absolute perfection hidden inside the most common thing on our planet, water. So, just read that again. Water boiling and freezing at the exact same time. Now, that sounds totally impossible, right? Like something out of a sci-fi movie? But get this, it's not science fiction. It's a very real and unbelievably important state of matter that's become a cornerstone for how we measure the world. So, this bizarre state has a name. It's called the triple point. It's this one-of-a-kind condition where you've got solid ice, liquid water, and water vapor all existing together perfectly happy in a stable balance. And we're not talking about some blink-and-you'll-miss-it phenomenon. Nope. It can stay that way indefinitely, as long as the conditions are just right. So the big question is, how on earth is that even possible? Well, it's not magic. It's all about the fundamental laws of physics, specifically thermodynamics. To really get it, we kind of need to look at the rule book that tells water how to behave. Think of it like this. Every substance has a map of moods, and we call it a phase diagram. It basically shows you that at these temperatures and pressures, water wants to be solid ice. And over here, it's happier as a liquid. And way up here, it's a gas. The lines you see on the map, those are the boundaries. That's where it's switching from one state to another. And this is where it gets really cool. On that entire map, there's only one single solitary spot where all three of those boundary lines, the one between solid and liquid, liquid and gas, and solid and gas, all cross paths. That one unique address on the map, well, that is the triple point. And there's even some slick math that proves just how special this point is. It's called Gibbs Phase Rule. It looks a little technical, but it's a super simple formula that tells you how much wiggle room a system has. How many things like temperature or pressure you can change before the whole system falls apart. So let's just plug in the numbers for our situation here. F is what we're solving for, the degrees of freedom, or that wiggle room I mentioned. C is the number of components. We're just dealing with pure water, so C is 1. Easy. P is the number of phases. At the triple point, we have solid, liquid, and gas, so P is 3. Okay, so let's do the math. 1 minus 3 plus 2 equals a big fat 0. 0 degrees of freedom. That means the system is completely locked in. You can't change the temperature, you can't change the pressure, not even a tiny bit without losing one of the phases. It is an absolutely fixed point. So, what do you do when you find something in nature that's so perfectly constant and you can make it again and again exactly the same way? Well, you use it as a benchmark, of course. Finding the triple point was like finding a North Star for thermometers. It was a total game changer for the science of measurement. See, before this, scientists were using things like the freezing or boiling points of water. But here's the problem. Those things change. If you're on a mountaintop, water boils at a lower temperature than it does at sea level because the air pressure is different. But the triple point, it couldn't care less about the air pressure outside. It's a single, absolute, unchangeable point, so much more precise. In fact, scientists were so confident in how stable it was, they assigned it an exact official value, 273.16 Kelvin. For context, that's just 1/100th of a degree above 0 Celsius. And for decades, that single perfect point was the fundamental definition for the entire Kelvin temperature scale. Okay, this all sounds great on paper, right? But how do scientists actually harness this thing? How do they create this state of perfection in a real-life laboratory? Well, it all happens inside a really elegant, carefully designed piece of glassware. It's a pretty meticulous process. First, you start with a sealed glass cell filled with ultra pure water. Then you use something super cold, like dry ice, to form this perfect little sleeve of ice right down the middle. After that, you just let it sit and relax until everything reaches a perfect, stable equilibrium. And for the final step, you melt just a tiny thin layer of that ice right against the inside wall. And boom, just like that, you've got it. Solid ice, liquid water, and water vapor, all hanging out together in perfect harmony, ready to calibrate the most sensitive thermometers in the world. Okay, so I get what you might be thinking. Cool science experiment for people in lab coats. But what does this have to do with me? Well, it turns out a lot. That level of precision actually trickles down into pretty much every corner of our modern world. Seriously, think about it. The thermometers that ensure the food you eat is safe, the ones used in developing life-saving medicines, the ones critical for manufacturing the computer chip inside your phone or laptop, and yeah, even the ones that help keep power plants running safely. They are all calibrated through a chain of measurements that, at its root, leads right back to this perfect constant that nature gave us. So, what's the future for our perfect point? As science keeps pushing forward, the way we define our most fundamental units of measurement tends to evolve too. And that's exactly what happened in 2018. The international scientific community officially redefined the Kelvin. So, instead of being based on a property of one specific substance, water, it's now tied directly to a fundamental constant of the universe itself, called the Boltzmann constant. It's kind of like how we no longer use a physical bar of metal to define a meter, we now define it by the speed of light, another universal constant. But, and this is a really big but, just because it's no longer the official definition, that does not mean the triple point has been retired. No way. In the real world, it's still the most practical, reliable, and accessible tool we have for producing a perfect temperature reference. It's still the absolute workhorse of temperature calibration all around the globe. When you think about it, the story of the triple point is just an amazing example of our ability to find these perfect little glitches in nature's matrix and use them to our advantage. It really makes you wonder, doesn't it? If we can nail down temperature this perfectly, what's next? What other fundamental constants are just waiting out there for us to discover and master?